We're going to look today at the constitutive equations of the different elements. On the screen you have a simple circuiting here that describes just a voltage source and it has a current here. Now, isn't it true that the basic law for this is that the voltage is equal to I times R? And here we have a mechanical resistor, which is in this case a damper, that we say that the force is equal to the constant V times the velocity. Yeah? See? These two equations are related in some way because this variable here and this variable over here both are like this E variable, the effort variable. So effort variable, how we say effort, is equal to, you have the constant in this case like this R and this B like this. These are the constant coefficient which we're going to call it R, and then the I and then the V are like this generalized variable which is the flow. Okay? When you have an equation like this, and you have the representation of the R element in here, like this. The output of this is the effort. So the bond graph is going to be like this. This is E and this is F. Therefore, the equation corresponds to this picture. However, if I have the equation the other way, if I put F is equal to 1 over R times E, then we have another situation, because what you have done in writing the equation this way is to say that the output is the flow. So this would be the way you represent this kind of element. So on a resistive element, we have two forms, this or this, depending on whether the output is an effort or the output is a flow. And let me say, Professor, how do you determine what's the output here? See, this is the element right here. The way you represent this is you say the signal that is all the way, you may say, outside of the R is the actual output. Like in this case, the output is E. See? And in this case, the output is F, because we have this equation. Again, this flow, and then this F. Yeah. So this is the constitutive equations one way or the other for the R element. So now I think we need to turn our attention in a simple way to the C elements or to the I element. So let's just do that. In this case, I am going to, perhaps it's a good idea we have something similar. No, we have here, but I am going to put a capacitor over here and the resistor over here like that, yeah? Okay. In this particular case, there we have this resistor here, and then you have this capacitor over here. So let's just put that one in there, or in a mechanical system, let's just do this, where you have a spring with a force. Yeah. So this is just as I did in the prior example. How are the constitutive laws of this? You already know that the voltage across the capacitor is going to be 1 over C times the integral of x dot dt, right? So this is 1 over c times the integral of so like this, or in this case, how about this? Better, yeah. And in this other case, you have that F is equal to the stiffness here, K, which is K times the integral of x dot dt, right? See, this equation and this one have the same form, but different variables at different energy domains. So if you have this equation here, it follows that you can represent it as we have done for the R element, represented it in the von Graph notation. So in this case, you will have C, the output is a voltage, so we have C like this. This is E and this is F. So it follows that from here, the constitutive equation would be E is equal to 1 over C times the integral of f dt, or this is the same as writing 1 over C times Q, where Q is the position, yeah? So also that the f dt, excuse me, that the Q dt is equal to F. These are the two constitutive equations of this element. Okay. In this case, for the circuit, we had that dV dt is equal to F, which is in this case di dt. Okay? No. F is di dt is what I'm trying to tell you. So let's just erase this for a moment right now. What I'm trying to say for this particular example is that I is equal to the Q dt. Yeah? Or the other way around, the Q dt is equal to I, consistent with this. So these two equations are the ones that control this form. But if you have the other form, we have it this way. This is C, and instead we have this.
What is F equal to?
Huh?
What is F equal to? Because D something over dt?
This one?
The alpha.
Is this one is the that F is di dt.
Okay.
No, F is equal to I. Yeah. So in here we have this is 1 over C, and that F is equal to I, or dq dt is equal to F. That's what I was writing.
So that's a
dq dt.
Okay.
Yeah. So in here, on this other one, you know for sure that the output is the flow. So if you have, even from here you could see that the flow in this case. The flow is equal to E times C, or alpha C times C times dE dt. This is F. That we also have in here that the Q dt is equal to F. And because of that, look what just happened. If you write the equation, differential equation, the Q dt is going to be equal to F, which is C times dE dt. This is a problem because a derivative we calculate has another derivative on the right hand side. So this one is integral form or integral causality, and this is derivative form. Derivative form. So this is for the C element, but and we gotta know that this will produce a differential equation like you see in here. I mean, this will produce a differential equation, but it has a derivative on the right hand side, and we can't have that to solve the system of equations because we have two derivatives on each side. So two derivatives on the equal sign. So we need to do a trial and error solution in case that we have derivative form. So we try to avoid that. Now let's change colors here, and then I'm gonna go to the I element. The I element, if you have it like this, it means the output is out of the I element. And in this case you have okay, so how do we write the equation here? The output is obviously is F, and this is E. So F is equal to what? 1 over I times E dt. And that we already know that dP dt is equal to E. So because of this, then it follows that dP dt is equal to the integral in this case, dP dt is equal to E. That's what we have. So we have a derivative on this side. But I'm trying to say is that if you have, let's just do this for now. If you had the I like this, okay, and then this is E and this is F. Okay, in this, what am I doing? I just do exactly the same way, and I need to draw it with a causal mark on the other side. This one right here, this would be E, and F over here. On this case, you say that E is equal to I times dF dt. We already knew this because the force is equal to the mass times the rate of change of momentum. So this would be dp dt in here. Okay, so we also know that dp dt is equal to E, so dp dt is equal to I dp dt is equal to E. I already wrote this, but dp dt is equal to I times df dt. Okay, so this is the integral form, and the other one is the derivative form. So far we have seen the three elements, and one thing I would like to do is if we can deal with the transformer elements, like a set of gears, for example. How can we do that? Take a look at this gear set that I'm just going to propose here. You have in here a torque 1, torque 1 and omega 1. Omega 1 is the rotation, okay? If you have this situation, you have a transformer element where the torque and initial velocity get transformed into a new torque and another angular velocity on the other gear set. So in here you have this gear with omega 2 and T1 omega 1, omega 2 and T sub 2. Any questions about this? If you have in here a torque and an angular velocity get transformed into another torque and another angular velocity. And in this case, in the case of the gear, it's just a gear ratio. So we could write this like this. And then so this is the, so if this is E sub 1 and F sub 1, this is E sub 2 and an F sub 2. Then it follows that E1 is equal to transformer modulus times E sub 2. And that this is E1. This is the other one in here that says F1 is equal to F sub C F1 times M is equal to F sub 2. This is the constitutive equation for this two-port element. Yeah. And now we need to do the constitutive equation for the GY element. And this could happen like this, but also the transformers could actually be the other way, like this. In general, you can have, depending on how it's connected, you can have it this way. And in that case, if this is E1 and this is E sub, this is E, yeah, in this case, you have this, it would be E sub 1 times the modulus equals to E2. Okay. This is the equation for the efforts, but the equation for the flow, you will find that F1 is consistent, so F okay, so F1 times, no, F sub 3 times M is F1. But yeah, okay, so that's in the transformer element. Now we need to do it for the gyrator elements. Gyrator elements are the ones that relate they are like transformers, but instead of relating effort to effort, they relate flow to effort. Yeah.
You're almost out of time on your recording.
Oh, thank you.